I am Anil Kumar. Welcome to my YouTube channel and the website globalmathinstitute.com. In this video, we'll discuss a very interesting topic, and that is to prove statements using the method of contradiction. The example which I have taken is to prove that we have infinitely many prime numbers. Well, we have infinitely many prime numbers, but now, how do we prove it? Well, first thing first, the statement is correct, and therefore, the method of contradiction can be applied. Now, what is the technique of applying this method of contradiction? I'll give you the basics here and then discuss all the details with the student and share with you soon. Well, basically, in the method of contradiction, we assume that the statement is not correct. And so we say that let contradictory statement be true. We call this statement as negative or negation. So in our example of infinitely many prime numbers, the negative statement or negation will be there are only finite number of prime numbers, correct? Now, if we prove that this particular statement, finite number of prime numbers, is incorrect, that means we have already shown, we have proven that we have infinitely many prime numbers. You get the idea. So that's the whole concept. So first step is to write the negative statement, and second step is to logically show that this statement is wrong. How do you show? That is a technique. But end result should be such that you yield something which is contrary or contradictory or something which is impossible. So if you get that, that means the assumption was wrong and the given statement was correct. Now in this particular case, the major difficulty with the students is how do they show that they have finite or infinite number of prime numbers? Because most of the students do not understand how do we generate prime numbers. You get the concept. So in spite of knowing the method of contradiction, they are not in a position to apply it. So we will also explore how to generate prime numbers. I hope you find it interesting. So look at the video and our approach to understand the method itself and the approach to prove the statement. So here is the class with our student Abby. Hi Amy, how are you doing?
Hi, sir. Yeah, I'm good, thank you. How are you?
Very good, very good. So how is the math going on?
Yeah, it's going okay. I feel like my test is tomorrow, so I feel like I'm just trying to like consolidate all the topics. It's fairly a lot when you look at it, but I'm just getting trying to get like all the formulas and stuff in my head. But there was a certain topic with proof that I didn't actually quite understand. So obviously there's the standard questions like prove that n squared is even and stuff like that. I kind of know how to get about that one. But there was one that was to do with like prime numbers and saying that there's an infinite number of prime numbers and prove that that's the case. So I was struggling to understand what that was trying to show and understand it.
So let us share the screen. If you have the question, you can share. Otherwise, just tell me the question. We'll work out the solution, right?
Yeah, I don't have the question, so
okay. Then
it's more of just a statement. So
here's the statement. So what is the statement once again?
So prove by contradiction that there are infinitely many prime numbers.
Okay, we'll do that. We'll do that. So let me just share a whiteboard with you, and then we'll begin from there. So all set for your test for tomorrow. I hope you are well prepared. And really expect, we expect very good marks from you. A lot of pressure on you.
Maybe.
Okay. So your topic is to, what you said is you want to prove that we have infinite number of prime numbers, correct?
Mhm.
Okay. And you need to prove it by contradiction.
Contradiction. Yeah.
Perfect. So whenever you want to prove by contradiction, what do you really get from the statement and what should be your approach? Can you tell me that?
So you would make an assumption that would obviously contradict the statement, and then you follow through with that, and then eventually you should contradict your assumption, which would therefore prove the statement is true.
Correct. So first thing is assume the statement is false.
False. Yeah.
So that means we are saying infinite number of prime numbers. So false will mean, so that means
It's a finite.
let the number of prime numbers be finite. Is that clear?
Yeah.
So let us say the prime numbers, finite numbers are like from P1, P2, P3 till Pn. Let's say that is the finite list of prime numbers, correct?
Yeah.
We have nothing more than that. So we have assumed that that statement is wrong, and therefore we have finite number of prime numbers. Now think about this. If I multiply all these numbers, what is product of these numbers? Product of these numbers will be P1 times P2, correct? Times P3
Yeah.
times TPN. When you multiply all of them, you get this product, right? Obviously, that product is a composite number. It is not a prime number, correct?
Yeah. Yeah.
Now see what happens when I add 1 to this. Then I get a number, correct? Is this number prime? Or
Yeah.
it has to be a prime number. n has to be a prime number as all other prime numbers are not its factor, as all other prime numbers, or as none of the other, I should say, as none of, as I should say, none of other, right? You get the idea?
But what happened if the P1 times P2 like that equaled 38?
Okay, I will show you.
And then plus 1.
Correct. So see, if I divide n by P1, it is not divisible since add 1 means n minus 1. Do you see that? There is one remainder.
Yeah.
I mean, it is not fully divisible.
Yeah.
If I divide by P3, P or any prime number which we have identified so far, none of them are able to divide n wholly, without remainder.
Yeah.
Because this one shows that none of them is a factor of n. You get the idea? None of them is a factor of n. But if n is a composite number, then one of them should have been there, right?
Yeah.
Since
So it's because of the plus 1, there will always be a remainder of 1.
There is a remainder of 1. You get the idea?
Yeah.
So that means n itself is a prime number.
I see. So n is a prime number.
Now that contradicts our assumption that only these are the prime numbers, right? You get the idea?
Yeah.
So that contradicts the assumption. Therefore, statement is true.
Yeah.
Now, it is a difficult concept to understand, as I'm seeing from the response, correct, from you? Think like this. I'll show you. I will show you a simple example, Amy.
I feel like when you like substitute it with numbers, it would be easier maybe.
Yeah. Let us say, do the, 2 is a prime number, right?
Yeah.
3 is a prime number. Multiply them. What do you get?
6.
How about 6 plus 1?
7.
It is a prime number. Do you see that?
Hmm.
Now see this. 2 times 3 times 5 is what?
30,
right?
Yeah.
Add 1 to it. 31. It is a prime number. Because 31 cannot be divided by 2, 3, or 5.
Oh, and that's always the case. Okay.
So it is not a composite number. If it is not a composite number, it has to be a prime number.
Yeah. This is only 2, one or the other.
Except for 1, right?
Yeah.
All other numbers are either prime or composite, correct? So you can take anything, right? You can say 2, 3, 5, 7, right? Multiply. So we multiply 7 and 30, we get what? 210, right? Add 1. 211 will be a prime number. You get the idea?
Right. And it's not divisible by any of those.
Any of these.
P2. Yeah. Okay. Yeah.
Therefore, that has to be a prime number. So this is the beauty of generating prime numbers by itself. You get the idea?
Yeah.
If you want to show, let us say, let me take an example, right? Let's say we have 101. Now we have to show that 101 is a prime number or not. Let us say we don't know, correct?
Yeah.
In that case, what are we going to do? What is square root of 100? 10, right?
10, yeah.
So that means if you divide this by numbers like 2, 3, 5, and 7, these are the only prime numbers below 10, correct?
Yeah.
They could divide this. So we know it cannot be divided by 2, it cannot be divided by 3, not by 5. Let's try by 7. 7 times 1 is 7, 31. So 7 doesn't go there, right? So therefore 101 is also prime number. Do you see that? Only by dividing with these 4 numbers, which are less than square root of the number.
Yeah. You prove it's a prime number.
It is a prime number. So to find, let us say 201, right?
Yeah.
211 was our number, right? So if I have to check whether 211 is a prime number or not, in that case, what I will do is, let's say up to 15, because 15 is, 225, correct?
Yeah.
So the prime numbers are 1, 2, 3, 5, 7, and then 11, correct? And then 13. Yeah. We'll try to divide this number by 11. It cannot be divided by 11 because it does not have that symmetry. Now with 13, you can try. So when you try by 13, 13 goes 1 times and you get what? You get 11, take away this is 81, right? 11, take away this is 8, and then bring down 1. Can 13 divide 81?
No.
13 times 7, it is 91. It cannot. Do you see that?
6. Yeah.
It cannot. And therefore, this is a prime number 211. Do you get the idea?
Oh, so it's like working backwards. If they said it proves that 101 is prime, you would do it like that.
You would do it like this. So any number given to you, what you could do is square root of that number, and let's say square root is x. All the prime numbers below x, you should try dividing that number with those prime numbers only.
Oh, right.
If you cannot divide, then that is a prime number.
Yeah.
So that is how we figure out whether the given number is prime or not.
Right. Okay. That's really clear.
I hope this is clear, absolutely clear, right?
It does. Thank you so much, sir.
Can you summarize what have you learned here?
Yes. So especially with the proof by contradiction, we've got that basic format of assuming that the statement is false. So in this case, we said assume that there is a finite number of prime numbers, and then we let like each prime number be like P1, P2, all the way up to Pn. That's what we're saying. But then if you do the product of all of them, just even like thinking about, when we did those tree diagrams and things, you'd have the prime numbers, and then when you multiply them all out, you get a composite number. But if we add 1 to that composite number, it has to be prime, because it's only like one or the other, like you said, except for 1. So then you get your prime number by adding 1, and then we say that whole thing is, we make it equal to like a number. So you said capital N, and then we found out that N has to be prime, and that none of the P1, P2 can be a factor of n. And so therefore you've contradicted the assumption that we made that there is a finite, so the statement's true.
Correct. So product of all the prime numbers, whichever you take, plus 1. If you do plus 1, you get another prime number.
Prime.
Remember that. So I shouldn't say consecutive prime numbers, but one after the other, the prime numbers which come in a sequence. If you put them and multiply them, then you get a number which is definitely a composite number. But if you add 1 to that, it becomes a prime number.
Oh, see, I didn't get that.
Whole series, as we started from 2, right? And tested it. Okay, so that was a wonderful question, and I hope you have understood the solution and must have benefited many of our viewers, right? Thanks for that question, Amy.
No worries, sir. Thank you so much.
Okay. So I hope you get the idea of how do we generate prime numbers. 2, 3, 5, 7, 11, 13 are the consecutive prime numbers, correct? 2 times 3 is 6. If you add 1, you get a prime number, which in this case is 7. Now let's take the first 3 prime numbers, 2, 3 and 5. 2 times 3 times 5 is 30. 6 times 5 is 30. If I add 1 to it, I get 31. 31 is a prime number. You get the idea. So the whole concept is that 31 cannot be divided by these prime numbers because that plus 1 is the remainder. Therefore, 31 itself is a prime number. So that is how we generate these prime numbers. And therefore, when we assume that there are n prime numbers, multiplying all the n prime numbers and adding 1 to it resulted into the next prime number, which was higher than any other previous prime number. And that shows that our list is not confined. We have another prime number, not just those finite prime numbers which we took. And that is how we show that the assumption was wrong. Since that negative statement, the negation was wrong, our statement that there are finitely many prime numbers is correct. And that is how we have proven the statement. Now in the next video, I'll talk about another example in which we'll say square root of 2 is an irrational number and will provide similar logic. So think over it. How do we show that square root of 2 is an irrational number? So think about it. How should we show that square root of 2 is an irrational number? For that matter, I could have taken any other radical also. I hope you find this series interesting and useful. Feel free to write your comments, share your views, and if you like and subscribe to my videos, that would be great. Thanks for your time and all the best.